On behalf of IEEE MTT-S Kerala Chapter, IEEE MTT-S Student Branch Chapter IIST, and IEEE EPS and MTT-S Student Branch Chapters of Government Engineering College Barton Hill, we welcome you all to the one-day workshop on millimeter wave and terahertz devices and technology, latest trends, and future directions. Now I hand over the virtual podium to Dr. Chinmay Saha sir, Chairperson, IEEE MTT-S Kerala Chapter for further proceedings. Thank you. Sir?
Chinmay, can you
Okay, sorry, I was.
she has handed over the podium to you.
Am I audible?
Yes, yes.
Okay. So, good morning, good afternoon, good evening to all the participants. So, I welcome all of you in this IEEE distinguished lecture, one-day workshop being organized by MTT-S Kerala chapter and IEEE IIST student branch MTT-S and EPS chapter in association with Government Engineering College Barton Hill MTT-S chapter. MTT-S Kerala started its journey in last year in 2019 with very ceremonial inauguration in presence of Professor Kaul, which is the Region 10 coordinator, and also Professor Siddiqui, Dr. Gautam Chattopadhyay. And we have been quite vibrant in doing various activities since then. So in 2019, we had a lot of physical events, but then this pandemic has made us think differently, do some improvisation. So we are having a lot of webinar events this year, 2020 March onwards. Recently, we inaugurated a new series, which is L4, Learn from Leaders and Learn from Legends. Needless to say that today's talks, all the speakers are of that quality, that caliber. So all these talks can also be termed as a L4 talks. L4 series was inaugurated by President-elect, and in presence of President Dr. Ala, and then Dr. Rashunda, Dr. Siddiqui, Professor Kaul, and etc. So we are quite vibrant, and we are really fortunate to have Dr. Song today. So I won't take much time today because today is the day to hear all the speakers. So initially, Professor Song agreed to come here when I communicated to him through MTTS portal, and it was planned as a physical event. But later on, we changed our plan, and then we thought because we are doing in virtual mode, for the benefit of the society, benefit of the young students, we'll have a few more speakers so that this becomes a one-day full event. So with this, we have another 3 speakers in pipeline after Song. So 2 talks are scheduled in morning and another couple of talks are scheduled in the evening. So that's the point of making it a full day workshop along with by clubbing the DL talk and other talks. We are very fortunate to have Professor Manoj as the leaders of IIST student branch. Professor Siddiqui has always been a mentor. I can see Dr. Shomak present over here, who is also an upcoming and young leader doing a lot of good activities, and we are fortunate to have young student volunteers in our chapter. So with this, I welcome all of you, and I sincerely believe that this is going to be a very eventful virtual day. And in future, we'll be looking forward to Professor Song's physical visit, and then we'll have a more interaction, physical interaction, maybe some chances to talk technically also, and look forward to have a very good technical friendship in future. Thank you very much again, Professor Song. Over to Sivada. Thank you all.
Thank you, sir. Now I invite Dr. D.S. Manoj, sir, to inaugurate this event formally. Thank you.
Morning, good afternoon, good evening, and a good day for everybody who is assembled here today. It's a very happy occasion for me and my membership at IEEE student branch at IIST. So this one-day workshop on millimeter wave and terahertz devices and technology, latest trends and future directions is a very special event because of 2 reasons. One reason is that this probably is one of the events that is culminating the year 2020. So the year 2020 was a very happening year, very important year because of several reasons. One, that due to the COVID-19 pandemic, all our routine, all our regular, our usual activities were disrupted. And while we faced all such disruptions, there was one thing that came as a big blessing, that is the opportunity to conduct virtual events, the the blessing in the form of experts who could deliver high quality lectures over the video, over online media to our membership. Usually, it would have been very difficult to get a distinguished lecturer hosted here, but because of the online possibilities, we were able to listen to top class speakers more often than before. So that was actually a blessing. It happened to all of the IEEE membership in the event of this pandemic COVID-19. The second reason why this workshop is very important is because it deals with two of the very advanced research areas in communication systems, communication engineering, and so on. That is, millimeter wave technology and terahertz devices. As you may be able to notice, the lectures assembled here by four of the very high quality speakers, Dr. Ho-Jin, Dr. KJ Vinod, Dr. Gaurav Banerjee, Dr. Kaushik Sen Gupta. You will get a flavor of the kind of advancement that they are going to talk about, especially at frequencies of 300 gigahertz, devices, packages, and systems, or the energy harvesting for Internet of Things, or circuit testing related challenges of RF and millimeter wave integrated circuits, or even the terahertz chip scale system. So, these are the areas that are actually going to influence the industry, influence the research directions, as well as make a significant advancement to the needs of future wireless communication systems. The need for capacity has been increasing substantially. The need for supporting large number of users has been growing beyond any particular limit. The kind of heterogeneous devices that need to access the internet through wireless medium has been increasing too. All these demand new directions of research, and that's where millimeter wave and terahertz devices point to us. I'm really glad to be here. I thank as well as welcome Dr. Ho-Jin Song, Dr. KJ Vinod, Dr. Gaurav Banerjee, Dr. Kaushik Sen Gupta to this event. All the members of IEEE MTT-S Kerala chapter, IEEE MTT-S student branch chapters of IAST, as well as Government Engineering College, Butterhill. Their effort has culminated in this event. I'm really glad to be here. I declare this event inaugurated. Thank you for this opportunity to be here today.
Thank you, sir. Now, I invite Dr. J.Y. Siddiqui, sir, from IEEE APS Regional Coordinator. He's from IRP Calcutta, and he's the virtual chair of the first Distinguished Microwave Lecture. So, sir, I hand over the virtual podium to you for further proceedings. Thank you, sir.
Thank you very much, Shivada, and good morning, everyone. I'm really grateful to Professor Manoj and Professor Chinmay for the commendable job that you're doing on behalf of MTT-S. And thank you, Dr. Song, for agreeing to this DL lecture. This MTT Kerala chapter, they're the most vibrant chapter in India right now. And, like inviting a DL, and that's a really commendable job, because most of the chapters that I have seen last few years forego and don't really take this opportunity of inviting DLs, and that's what the society provides. That's for the benefit of the society members. And I'm glad that you are showing the path to all the other chapters in the region. Without much ado, I welcome Dr. Song, and I'll just talk briefly about his biography of Dr. Song. Dr. Ho-Jin Song, he received his base degree in electronics engineering from Kyungpook National University, Daegu, Korea in 1999, and an MS and PhD degree in electrical engineering from Gwangju Institute of Science and Technology, Gwangju, Korea in 2001 and 2005 respectively. He joined Nippon Telegraph and Telephone Japan in 2006, the third largest telecommunication company in the world, and was engaged in development of sub-millimeter and terahertz wave devices, circuits, and systems for communication, remote sensing, and imaging applications. In 2015, he was named to be the Distinguished Research Scientist of NTT Labs. Since 2016, Dr. Song has been with the Department of Electrical Engineering, Pohang University of Science and Technology, known as POSTECH, in Korea, and is now the director of Millimeter and Terahertz Radio System Research Center in POSTECH under the support of the Korean government. His current research interest includes millimeter wave and terahertz circuits, packages, and testbed systems, particularly for wireless and radar applications. Dr. Song is a recipient of the GIST Best Thesis Award in 2005, NTT Microsystem Labs Research Award 2009 and 2014, and the recipient of the Young Scientist Award of Spectroscopical Society of Japan, IEEE Microwave and Wireless Component Letters, Tatsu Ito Best Paper Award, and Best Industrial Paper Award at IEEE MTT-S IMS in 2016. He's a senior member of IEEE and an IEEE Distribution Microwave Lecturer for the term for the years to 2019 to 21 term. Again, I welcome Dr. Song, and your talk will be for 1 hour, and the rest of after that we'll have some brief interaction with the students. Thank you. Please, you may start your talk. Thank you.
Okay, thank you very much for your kind introduction, and I'm really pleased to have a chance to deliver my talk in this virtual way. But anyway, somehow I'm very sorry I'm not able to physically visit your place this year. But anyway, I hope you and your family's health even in these COVID situations. Okay, today I prepared a lot of slides, and also the title of my talk today is Terahertz communication system at 300 gigahertz, and then actually I'm going to talk about what we did in terms of device, package, and system when we developed this kind of Terahertz communication prototype. Okay. Okay. Before getting into detail, I'd like to give my special thanks to my colleagues in Japan and Korea. And here is a brief agenda of my talk today. So first of all, I'd like to give you some background of the Terahertz communication system, or why we are so interested in Terahertz wave for communication applications. And also, we share. Do you have any problem with my voice or slide? Is it okay?
It's
okay.
All right. Okay, thank you. So, and then I will move on to what we did actually. So I'm going to present a little more detail of the first full system demonstration in Kiosk data download system of the Terahertz communication prototype. So actually the system is operating with ASK data modulations and at up to 20 gigabit per second. Actually, when we developed the system, we have faced several actually technical challenges in terms of package and system point of view. So I'm going to share those issues with you, and I'd like to give you a couple of examples how we overcome those issues. And then before concluding my talk, I will give you my own some future perspective in Terahertz communication system. Particularly, you may know that these days the 5G communication system just has been released worldwide, and right at that time, the research community is now looking at the next cellular communication system, which is usually called 6G communication system. And the many people believe that the Terahertz electronics or Terahertz application, Terahertz system technology would be one key enabling technology for 6G wireless communication system. So in that perspective, my future perspective will be a little bit helpful to your future research. Okay, so I believe that you may have a chance to heard about the terahertz waves. So usually in IEEE, terahertz wave is left to frequency range in 300 to 3 terahertz. 3 terahertz. But in general, we used to say the terahertz waves in 100 to 10 terahertz. But any important one is that, as you can see here, the terahertz wave is located right between the microwave and the light wave in electromagnetic spectrum, meaning that the terahertz wave may behave in some part microwave-like or in some part light wave-like. For example, the terahertz wave has very strong interactions with many molecules, particularly the rotational, vibrational, or transitional spectroscopic fingerprint is very strong at terahertz spectrums, particularly for large size molecules. On the other hand, in the wavelength perspective, the terahertz wave will provide much shorter wavelengths than the millimeter wave, so that if we utilize this terahertz wave in the radio or imaging system, we are able to have much fine or high resolution imagings. And also by combining these two characteristics, we are able to detect some concealed materials based on the high resolution imaging of a spectroscopic fingerprint. So even with such a very unique and very nice characteristics, it was very hard to use terahertz wave for practical applications. That's because actually it was very hard to produce high enough radiations from any sort of devices. For example, here I plotted a couple of electronic devices along with light wave devices, photonic devices. So as you can see, as frequency increases, the output power from electronics will degrade a lot, and also as wavelengths be longer, the output power from photonic devices are degraded a lot. So because of this property, we used to say that, we used to say this frequency region as a forbidden region for a long time. So generally, any sort of electromagnetic system, including radio imaging system or communication system, once we need to radiate the electromagnetic wave into the air, and we need to detect or receive the reflected or transparent or transmitted signal with a high sensitivity. But once we fail to generate the high enough powers, then there is no way to maintain high enough signal to noise ratio that is required for the high throughput or high quality imagings or high quality spectroscopic analysis. So in that point of view, the lack of the high power transmitter was one of the biggest obstacles for a long time. But nevertheless, the many scientists, particularly in communication societies, are very interested in this terahertz waveband for the communication applications. That's because of one very unique features of the very huge bandwidth at terahertz frequencies. That's because, for example, here is one photos of the two basketball players. One is very tall and the other one is relatively small. So for example, in case of the basketball players, the height is one of the key requirements for good players. Of course, there are many other key requirements such as speed or strength, which is very important for, the top class or top tier NBA players. But if you are scouters of any NBA teams, then you may select this tall guy rather than the small one. That's because, as you may know, that in case of speed or strength, those property or those characteristics can be earned or improved by practice or exercise, or even the medical treatment. But in case of the height, there is no way you can increase or you can enhance those properties. So that's, I mean, the height is, the bandwidth is something like the height for the NBA players. So in case of the bandwidth, if you have some specific bandwidth allowed from your government or international society, then there is no way to use more than that frequency band allocated to you. So usually those available bandwidth is correspond to the carrier frequency. So in case of you operate the system at 300 gigahertz, and if we assume, for example, the 1% fractional bandwidth, then compared to the 3G or 4G cellular system, you may or we may able to use at least 150 times larger bandwidth than the other cellular communication system, which means that we are able to deliver 115 times larger data, or we can make the system in more simple way. That is a key, or that is a reason why we are so interested in terahertz frequencies for communication purpose. Actually, the theory is very well proved by very traditional theory, which is called the Shannon theorem. So as you can see in this formula and graph, the maximum data capacity of given wireless channel, or even for any channels, the maximum data capacity is simply bounded by the bandwidth of the channel and the signal to noise ratio provided by transmitter and receivers. So for example, if we increase the bandwidth, of course, we can increase the data capacity. And also if we increase the signal to noise ratio, yes, surely the data capacity can be improved a lot. But as you can see here, so once the increasing the signal to noise ratio is now the measure of the low scale in this equation, so that increasing bandwidth is more effective to the increasing the signal to noise ratio. On the other hand, as I said before, generating high enough power at terahertz frequency is yet very challenging, which means that it is quite hard to produce or hard to secure the high signal to noise ratio. Otherwise, the large bandwidth is inherently provided by with a very high carrier frequencies. Of course, some of you may worry about the attenuation loss in the air. That is quite true, because many air gases such as water or oxygen interact with high frequency signals, so that the many electromagnetic can be observed by those gases. So here is, for example, I plotted the attenuation loss at up to 3 terahertz, and as you can see, there are many peaky absorption lines all correspond to the water or oxygen or many other gases. But if we zoom down below 1 terahertz, you can see, of course, there are a few absorption lines, but we can see very clear electromagnetic windows right between the absorption lines, and I summarize those windows in this table. So as you can see here, for example, if we are using the 300 gigahertz band, then the frequency window of around 40 gigahertz would be provided. At that time, the attenuation loss by the waters, even with the very heavy rain conditions, the attenuation loss would be much less than 0.1 dB per meter. Meaning that if the system is used for quite short range or middle range applications, then the attenuation loss in the air will be a big problem. For example, in case of the 1 meter long distance, the attenuation loss by those, for example, water, will be less than 0.1 dB. Even in the case of 100 meter long distance, then the attenuation loss by the air would be just around 10 dB or much less than that. Then compared to the other, the attenuation factors in transmitter and receivers, such a loss from the air is quite negligible. Meaning that what I want to say is there are huge spectral windows we can use with the NOVIC interference with other applications. Another important one here is that, for example, I said that at 300 gigahertz band, the 40 gigahertz bandwidth would be available. Do you have any ideas how many or how large bandwidth we are now using in this planet for communication purpose? For example, the 4G system in Korea occupies around the 80 megahertz bandwidth. In case of the 5G, it is allowed to use around the 400 megahertz. And also, according to the standardization document, at up to 800 megahertz would be available for 4G applications. And 60 gigahertz radios are allowed to use around the 9 gigahertz bandwidth, actually as far as I know, which is the most largest allowed bandwidth for communications. And also in the world, there are many other applications for military or universal or satellite communication system, but all those occupying bandwidth is much narrower than the cellular communication system. So what I'm saying here is that the entire frequencies we are now using for communication system in this planet is much less than 150 gigahertz. But as you can see here, the single frequency window at Terahertz frequencies would provide, for example, the 3 times or 4 times larger than that of the entire frequency band in this planet. So we can deliver almost all data with the wireless manners in single communication channels. So there is a biggest potential or big point why we are so interested in Terahertz communication system. Of course, we can do many things with the Terahertz communication system. For example, the Wi-Fi or last 1 mile system, last 1 mile communication system is one maybe predictable applications. And also something new applications such as a Kiosk data download system. Actually, I'm going to present the detail of this application later. And also, even in the 5G communication system, the new wireless link is required, which is usually called the backhaul or fronthaul system. That's because in case of 5G system, the single antenna station should provide or expected to provide more than 100 gigabit per second data rate to provide multiple users at once. Meaning that we need to install any very high-speed data feeding network to the single antennas. And the other problem of 5G system, particularly at the millimeter wave system, is because of very high attenuation loss or very relatively low signal to noise ratio at 28 gigahertz, the distance between antenna stations should be around 100 meters or less, meaning that the density of antenna station is dramatically increased against the 4G system. So in case of the 4G system, all the antenna stations are fed by fiber optic network. But in case of the 4G system, it looks quite hard to do that because we need a lot of trench constructions to feed all those antenna stations separated by around 100 meter long distance. Then many people are thinking to avoid such a massive grounded constructions. The one possible solution is to feed those antenna stations with a wireless meter. So in order to do that, the wireless communication, or wireless link channel, feeding channel should provide up to 100 gigabit per second or even more. Then how to do that? Then simply speaking, we need more bandwidth or we need more data capacity. So then the Terahertz frequencies would the only band spectral resources that can provide such a high data capacity. So in addition to that, I'm going to briefly talk about the other two very attractive applications for Terahertz communication system. The other one is data center wireless communication system. So as you may know that these days, almost all data are actually coming into the data center operated by Google or Amazon or many other local operators. And the size of data center is a little bit huge, and the number of servers installed in that center is really, the millions number of servers are installed in single site. The problem is that all the servers in the data centers are interconnected via plastic fibers, and it actually causes a very massive and intensive maintenance effort. So in order to replace or in order to reduce such a maintenance effort, some people are thinking to replace those plastic fibers with a wireless communication system. So in order to do that, once again, we need to actually the main role of plastic fibers between servers is to interconnect with very high data capacity. So considering those specifications or requirements, the new wireless communication system between the servers should also provide very high data capacity. So in order to do it, again, the high frequency or terahertz frequency would be the only options. And also, do you know that the your personal computers actually requires multiple terabit per second data link right between CPU and memories. So these days, data bandwidth between CPU and memories already exceed 5 gigabit per second for newest personal computer system. But all those links are now based on very low-cost printed circuit board technology. So as you know that because of very low, very high dielectric loss of low-cost PCB materials and also low-cost copper materials, so the 5 terabit per second data capacity is already much exceed the maximum limit of those low-cost PCB technology. So when people think to replace those PCB with fiber optic technology, and the other people some people also think to replace those PCB with wireless technology. So Intel tried to replace PCB with optical technology many years ago, and I'm not sure that such a let's say the optical PCB is really available or not. But these days, another people's actually demonstrated a very high data capacity between such a very short link distance between CPU and memory, and they found that such a very high data capacity wireless link is really feasible in terms of the spectral resources that can be provided by terahertz frequencies. So regardless the link distance for 6E or the long haul distance communications, such a very short distance, for example, the data centers or device to device communications is would be another very good key applications of terahertz communication system. And how fast data rate is available for us. So technically, I'm not sure that how high data rate can be achieved at terahertz frequencies, but on the other hand, if we really look at this graph, which is about the technical progress trend of wireline and wireless communication system. So as you can see, the progress speed of wireline is much slower than that of a wireless communication system, and we can easily estimate that one day the data capacity of both technology would be crossed in near future. And actually, the cross point would be is actually estimated from this plot to be around 100 gigabit per second in 2013. So meaning that in order to accommodate the recent technical trend shown in this I'm sorry. I'm sorry. Okay. My iPhone is a response to my talk. I'm sorry. So anyway, so the 100 gigabit per second would be technically necessary in near futures. And also considering the recent very explosive increase of data traffic, particularly in the mobile devices, we also need to have some new wireless technology which can handle all those explosive increasing data traffic in somehow. Then let's assume we are now thinking about the 100 gigabit per second in near futures. Then how to do that technically? There are numerous ways to achieve that because of the data capacity can be determined by 3 key factors according to the communication theory. So for example, the number of antennas and bandwidth and the modulation scheme can define the data capacity of a given system. So in order to get the 100 gigabit per second, one people may think about the 1 gigahertz bandwidth with a very high demodulation scheme with a many number of antennas to get the 80 gigabit per second data rate. So for my case, I would use a little bit larger bandwidth of around 50 gigahertz with a very simple modulation scheme of QPSK with a single antenna to get the 100 gigabit per second. I'm not sure that which approach is a more feasible or technically reasonable, but I'd like to show you the second option would be quite has a very strong potential for in near future because of these days the Terahertz technology and particularly the device and the packaging technology has been improved day by day, so that the physical devices can provide very huge bandwidth, so that and also considering power consumptions from the signal processing required for very high, very complex modulation scheme and the minor technology, then the very analog-based, very wide band communication system would be a much stronger option than the other one. Then again, what is the key problem? So what I'm saying here is that the reason why we are so interested in Terahertz communication system, or why we believe that Terahertz frequency is the only option to get the 100 gigabit per second, is the very huge bandwidth which we can have at very high Terahertz frequencies. Then the older system should be developed to get very high or very wide bandwidth. As far as I know, the first data transmissions at Terahertz frequencies has been demonstrated in 2004 by one German group. So at that time, the German team utilized the Terahertz spectroscopic system, actually, which is called the time domain spectroscopic system, driven by a very expensive and bulky femtosecond laser system. So the photoconductive antenna driven by femtosecond laser can produce the Terahertz pulses into the air. And then this German research team inserted one dedicated devices, which is called two-dimensional electron gas modulators between the transmitter and receivers. And then, so based on this system, they were able to transmit around 7 kHz audio signal from transmitter and receivers with a wireless manner. The problem was that the maximum data capacity or maximum data bandwidth was just around 7 kilohertz, not the megahertz or gigahertz. That's because of the very limited modulation bandwidth of these modulating devices, meaning that the electromagnetic spectrum at Terahertz wave can provide very huge bandwidth, but if we fail to utilize such a huge bandwidth with dedicated devices or system, we cannot get such a high data rate. We are amazing. So after that, the many research groups worldwide try to demonstrate the feasibility of Terahertz communication system with a very dedicated or very specially designed devices. And in my group, we try to prove the feasibility of Terahertz communication system with fiber optic devices. So actually, here is one brief experiment. Actually, the transmitters that consist of 2 laser diode and electromagnetic optical modulators, and photomixers that can translate the Terahertz photonic signal into the Terahertz electronic signal. And to do that, we need a very high performance photomixers, to produce a high enough Terahertz signals. So in case of the UTC-PD, that was produced by developed in my group. Maximum output power was around -3 dBm at 300 GHz band, and also the available bandwidth with this device was around 120 GHz, 120 GHz, which is almost 3 or 4 times larger than that of the other Terahertz devices at the time. So anyway, and also for the receivers, we prepared very simple receivers. So for example, here, actually the receiver is very simple, the envelope detector receivers. So single diode, Schottky-Weber diode was integrated along with the integrated slot ring antennas. So, and also please note that there was no amplifiers in front of the diode detectors, or type detectors, meaning that the system or the receiver is quite far from the contemporary receiver system using wireless communication, region wireless communication system. So here is the result. So as you can see here, with this very simple system, we were able to get 24 gigabit per second error-free data transmissions. At the time, the distance was not that long because of very low power and a very low sensitivity. But anyway, important one is that the output powers in this setup was just around 100 microwatt. And also, please note that there was no amplifier at all in receivers. And also, modulation scheme was just OOK or ASK, which is known for very inefficient modulation scheme. So even with this very, let's say, very poor numbers in terms of transmitting power or receiving noise figures and in terms of spectral efficiency, we were able to get 24 gigabit per second, which is, as far as I know, the large data rate which was demonstrated in any frequency range at the time in 2010 or 2012. Then what is the reason how we get this high data rate? That is because of the huge bandwidth at Terahertz frequencies. Because of huge bandwidth, and we were able to utilize such a huge bandwidth to deliver data from one point to the other point, we were able to get 24 gigabit per second. So again, the very key point at Terahertz frequency communication system is how to utilize such a huge bandwidth provided at that high frequencies. But problem is that, so this is actually the experimental setup we used for the experiment for the result I presented right before. So problem is, so as you can see here, the experimental setup is very bulky and very big. So this is not what we want for commercial communication system. So at least we need to install such a Terahertz transmitter and receivers in smartphone or many other mobile devices. So in order to do that, we need many enabling technologies such as devices and also circuit design and packaging and antenna should be developed for a very compact one. And also the physical layer should be maybe redesigned to accommodate a very huge bandwidth characteristic of Terahertz communication system. So from now on, I'm going to briefly review what was going on worldwide in terms of device circuit design and all these issues one by one. Okay, first of all, here is one very short summary of 35 electronic devices in terms of the maximum oscillation frequencies with respect to the reported time. So as you can see here, so now we are now living in, actually now it is the end of 2012, 20, and around 10 years ago, actually maybe around 12 years ago, the maximum oscillation frequency of very state-of-the-art 35 electronic devices exceed 1 terahertz. So for example, the Northrop Grumman and Fraunhofer in Germany and Teledyne company in United States already reported 1 terahertz electronic devices, actually transistors, 35 based transistors. And also NTT Japan, my group, reported 1 terahertz HAMT devices at 2015. And also the silicon-based silicon germanium HBT has been reported for around the 700 gigahertz maximum operation frequencies at 2017. So meaning that the Terahertz frequency is not that far from our hand, because the already very high speed, or let's say the Terahertz transistors are technically available. So with those devices, there has been many reported in MMIC or RFICs. For example, the 500 gigahertz amplifiers and the 300 gigahertz power amplifier has been reported in 2011 and 2010. and also many other functional components for which is required for communication systems, such as functional fundamental oscillators, frequency dividers, and the frequency locked loop or phase locked loop, and also another very high gain amplifier. All those functional components have been reported in 10 years ago. So right at that time, I mean around 10 years ago, my group started to develop the first full system demonstration in Kiosk data download system. Then probably before getting to the detail, I need to explain what is Kiosk data download system. So the Kiosk data download system is something like data vending machines. For example, here is one, let's say, a drink or a snack vending machine. So in order to use that, once you need to approach to the machine and then insert your coin and then select one product you like to buy or you like to eat. Then finally the item will be, let's say, provided instantaneously. The data vending machine is something like that. So because of some reason, you need to download or you need to have some data from the cloud or from your servers or your personal computers in your office or house. Then once you need to approach to this kind of data vending machines, and once you pay and make some transaction to allocate the data downloading, then in a couple of seconds, all data you need to would be instantaneously downloaded to your smartphone. So that is the basic imaging of the Kiosk data download system. So here is another view of the Kiosk data download system, the using of the Kiosk system. So in this case, probably we can technically characterize the transmitter as a stationary, and the transmitter can be connected to the fiber optic network, to be fed a very huge amount of data from the core cloud servers or the other personal computers in your office or house. By the way, on the other hand, the receiver should be very compact. For example, the mobile receiver is very required. In order to do that, the small form factor and very low power consumption is required. And also, the link distance only exceed 1 meter long distance, considering the use case of this kind of the Kiosk system. And also, in terms of the multiplexing schemes, it is no doubt the system will work in the peer-to-peer link system. So that based on this kind of the technical characteristic or requirement, we start to develop the system. So before at very first time, we try to figure out such a system is really technically feasible or not. So we have conducted very simple link budget calculations with some target numbers. For example, the output power of around 10 dBm at 300 gigahertz, and the noise figure of around 15 dB with 10 dB system margin. So with these numbers, we found that even with no signal processing for feed-forward error collections, the 20 gigabit per second data rate, actually the error-free data rate, would be feasible if we select the antenna gain, the total antenna gain from transmitter and receiver more than 50 dBi. So let's speaking the 25 dBi for transmitter and receiver respectively. Probably if you are familiar with microwave system, then 25 dBi antenna gain is very huge, and the aperture size is really huge. But considering very short wavelengths of, for example, 300 gigahertz, then the 25 dBi horn antenna is very compact. But the diameter of the horn antenna is much smaller than your pencils or your fingers. So considering those one, the that Kiosk Terahertz communication system would be feasible technically. So we decide that. So here is a block diagram of the entire configurations. So here, green one is a transmitter chain, and the purple one is a receiver chain. And in order to incorporate the Terahertz Kiosk data download system with the fiber optic communication system, we decided to use the 10 gigabit Ethernet system. So we combined the two channel of 10G Ethernet system to make a 20 gigabit per second data stream. And also in receivers, we divided the received 20 gigabit per second data stream with a dedicated demux module to feed the two channel of the 10G Ethernet system. So final demonstration has been demonstrated along with this commercially available gigabit Ethernet system. Okay, so as I said before, in order to develop ones, we need a very state-of-the-art, we need a very high-speed electronic devices or photonic devices anyway. So in our cases, we try to develop the system with the electronics approaches. So in order to do that, first we developed the 70 nanometer 70 nanometer power HAMT devices. So in order to get the high enough powers or high powers from these very nanoscale transistors, we designed we very carefully designed the architectural layers of the HAMT devices. So with that such a careful design, we were able to get very high breakdown voltage, and also at the time the maximum oscillation frequency was around 700 gigahertz. And also you know that because of very short wavelengths at Terahertz frequencies, many of the electromagnetic wave in MMIC can be accumulated in substrate because of very high dielectric constants. So in order to suppress that, we need to once thin down the substrate down to 50 micrometers at 300 gigahertz applications. And also in order to suppress the substrate mode, then we need to add the very high density via substrate via hole. So here is electroscopic photos of the very thin substrate and also very high density via hole. All this one is very carefully designed in order not to cause any physical failure when you design, when you packaging this MMIC in practical system. So here is an example of the power amplifier. As far as I know, this one is a second generation power amplifier. So in order to get very high output powers of around 10 dBm, we targeted the 12 stage, actually 12 stage in series and 8 stage in parallel power amplifier has been developed. So by carefully designing these power combining structures, we were able to get around 10% fractional bandwidth at 300 gigahertz. And also the gain was not that bad, around 15 dB. But one big problem was that the power, in terms of power consumptions, this amplifier displayed around 1.3 watt for 10 dBm output powers, which means that the energy efficiency of this amplifier at maximum power was less than 1%. More than the 99% of driven energy from DC side was actually dissipated by heat. So that actually this heat problem can cause very serious reliability issues in practical applications, so that we need to pay more attention to that issues. Actually, in our system, because of the heat problem I mentioned before, the power amplifier had to package it into this kind of metallic waveguide packaging. So because of this metallic one is quite advantageous to sink out the heat generated by the power amplifiers. Probably I may have short time to show the detail of this power amplifier waveguide module later. And also in case of modulators, the configuration is very simple. So we utilize the distributed shunt switch topology in order to get very wide enough modulation bandwidth. And thanks to very careful design of this, or very careful consideration on this feedback path through these feedback capacitors, we were able to get very broadband or broad group delay property in the system. In case of the receivers, in case of the amplifier or transmitters, we need to take care of the modulation bandwidth, or we need to take care of the heat from the power amplifier. But in case of receivers, the such a, let's say, a nonlinear effect is not that a serious problem, so that we were able to integrate everything into single chip. So as you can see here is the dipole antenna and 3-stage amplifier and the HBT detectors along with the data amplifier. All these components has been integrated into single chip. And in my memory, the size of this single chip MMIC was around 0.8 and 1.2 millimeters. And because of this on-chip or integrated antennas, we are able to integrate the MMIC along with the silicon lens in order to increase the directivity. So here is the first generation packaging of the receiver side, and I will show you the second generations for very compact one. So when we present this kind of slide, many people worry about how to design such a high frequency, even passive circuit, but you don't need to worry about that because commercially available FEM or FTD based simulator actually provides very high accuracy even at high frequencies. The only problem is that how you model the material parameters at these high frequencies. In order to do that, probably you need to have a couple of try and error challenges, but these days there are numerous materials and numerous literatures that report the material parameters of many electronic materials, so that based on those ones you are able to get very high accurate simulation result. Okay, the receiver amplifier provides around 24 dB gain over 10% fractional bandwidth, and here is a photo of the first demonstrations. So as you can see here is a transmitter, and here is a receivers, and we change the distance and measure the bit error rate along with the distance. And as you can see here, the recovered eye diagram shows very clean and open eye, and the measured VR was much less than 10 to the minus 8 at up to 1 meter long distance, meaning that please note that we didn't use any sort of signal processing in this experiment, and I'd like to show you one video clip. Okay, so this green dot means the distance, the black line means 0.9 meter long distance, and because the receiver is moving backward, you are now seeing the eye diagram delaying in real time. So as you can see here, at up to 1 meter long distance, we can see very clean open eye diagram recovered from the receivers. And based on those first prototype, we have developed the second generation system actually for the final proof of concept demonstrations. So for the transmitters, we integrated the transmitter side in the middle of this transmitter machine. And for the, to demonstrate the mobile transmitter receivers, we installed this receiver packaging into the handheld receiver mockup. And, to make sure the system work in very reliable manners, we have developed the FPGA-based forward error collection board. And so this actually FPGA board will work as a data mux and demux function. And here is another video clip of the final proof of concept demonstrations. Okay, so what we are seeing here is that once he places his smartphone on top of the transmitters, and the first click is about the payment, and the second click is about the data he like to download. And then after waiting for a few seconds, the final data download has been completed. In this experiment, the size of data we downloaded was around 17 gigabyte, 17 gigabyte, which is very huge one. So to download such a 17 gigabyte data, it took around 7 seconds. Just 7 seconds actually spent to download the 17 gigabyte from transmitter to mobile receivers in wireless manner. So it is very, I guess, the very important result we achieved, and we achieved in last time. But there is a couple of serious problems. That the biggest one is this kind of the metallic block packaging. So as I said before, once we need to install, or we need to install such a Terahertz, let's say the transmitter or receiver MMIC into very compact the smartphone or very small mobile devices, then in order to do that, such a very bulky and heavy metallic packaging is not that feasible. Or and another biggest problem is in order to demonstrate such a very metallic bulky metallic one, we need a very cumbersome the packaging technique, particularly the in case of the wire bonding one. Physically, we can make the wire bond as short as possible, but electrically it is too long at 300 gigahertz. So because of really physically, electrically long wavelengths, we are not able to avoid very high inductance that cause very high mismatches between the MMIC and the external the substrate for the waveguide packaging. So in order to avoid that, we thought that we had some ideas about the quasi-optical packaging. So because the Terahertz wave is right between the microwave and the light wave frequencies, probably we thought that we are able to use quasi-optical one, such as the LED packaging. In case of the LED packaging, actually the very low-cost LED packaging, the dedicated LED devices should be located right between, in the middle of the carrier that provides an electrode simply, and then we cover those carrier electrode with a plastic lens in order to collimate the light wave from the LED chips. So we did the same thing at Terahertz frequencies. We prepared the carrier structures or carrier electrode with the LTC's technology, and also we mounted the MMIC, which is integrated with the on-chip antennas on the middle of the carrier with the flip chip bonding technique. And then finally, we placed the silicone lens on the backside of the MMIC. And here is the prototype of the receiver one. So as you can see here, simply by using a quasi-optic technique or quasi-optical packaging technique, which is commonly used in the very low-cost LED packaging, you were able to get very compact but very high performance receiver Terahertz devices or device module. So here is another experiment result with this very compact receiver module. So as you can see here, please note that in this packaging, we didn't do anything in Terahertz wave paths because we did use the same silicone lens in the Terahertz wave paths and in the waveguide, in the electrode side, no high frequency pass through these structures, so that there is no way to have any degradations at high frequencies, meaning that the final result is almost identical to that of the other very bulky devices. And also another very interesting idea is about this kind of the, let's say, horn antenna structures in the plastic packaging materials. So in case we made this kind of the plastic shaped air hole in the backside of the plastic packaging, and in order to make a test in waveguide structure test setup, we made another waveguide structures in the backside, the other backside of the structures. The important one is that simply by making this kind of the pyramid structures, we were able to get very high antenna gain over very broadband frequencies. Please note that the length of, let's say, the length of the antenna at this time was just around 2.7 millimeters. 2.7 millimeter horn antenna, let's say plastic horn antenna, provided more than 17 dBi antenna gain at 300 years. So it is very amazing, but considering very fundamental theory of electromagnetic engineering, this kind of structure is very easy and quite compact, so that and also because of no materials lead to the conductive loss and the dielectric loss, it obviously provides a very high antenna gain. So probably you can utilize this one as a future Terahertz communication, future Terahertz device packaging. So here is another prototype, and according to this experiment, we will found that even in this kind of very low-cost packaging system, the estimated transitional loss from MMIC to this outer electrode would be around 1.5 dB at 300 GHz. This is quite amazing numbers. Then the remaining question is, in previous experiment, I showed you that 20 gigabit per second error-free data transmission in Kiosk data download system. But at very first time, I told that the 100 gigabit per second would be feasible at Terahertz frequencies. So in order to achieve that, we developed the QPSK, the modulator and demodulator MMICs, and we experimentally demonstrate that 50 gigabit per second. Simply by we increased the spectral efficiency from 1 to 2, so that the achieved data rate was doubled from 20 to around 50 gigabit per second. Again, we didn't use any signal processing to get these very good BR numbers. And by increasing the data rate, by increasing the number of modulations with from QPSK to 16 com, we were able to finally get the 100 gigabit per second at up to 2.4 meter long distance. Of course, at that time, the single device, performance of single device such as a power amplifier, modulator, and demodulator or down conversion mixer has been improved a lot. And thanks to such a performance improvement and a high signal to noise ratio, we were able to get, or we were able to utilize such a 16 com complicated waveform over a longer distance. But anyway, by using a similar technology to improve the device device performance, it is quite feasible to get the 100 gigabit per second data rate even at this moment, or even with currently available technology. Okay, then before summarizing my talk, I'd like to give you some couple of latest news from the other groups. So up to now, I presented a couple of the results of the Terahertz communication system that is based on the 3.5 electronics. But according to the latest literatures reported in the ISSCC by Hiroshima University, they actually presented silicon-based or CMOS-based 300 gigahertz transmitters, and they proved that that silicon-based transmitter can provide around 100 gigabit per second wireless transmissions. Of course, at the time, the transmission distance was very short, but it's very remarkable because very low-cost silicon technology can also be utilized for Terahertz communication system. Another good news is from my group, even with the 65 nanometer CMOS technology, we are able to get the 10 dB gain at 300 gigahertz. So here is a photo of the RFIC. So three-stage RFIC can provide around 12 dB and 9 dB power gain at around 28 gigahertz and 300 gigahertz. We didn't use anything special, but please note that the only thing we did in this research is we applied very dedicated circuit design topology. Actually, in order to accommodate or in order to deal with very high signal loss even in the RFICs, we actually add some positive feedback paths in order to compensate for the huge loss in the microstrip line structures. So by using that, of course, we need to pay lots of attention in order not to make the RFIC oscillate at the high gain mode. But by careful design, actually allow us to get this kind of reliable gain at 300 gigahertz. Okay, I'd like to conclude my talk here. So I presented a 20 gigabit per second Kiosk data download system and even 100 gigabit per second data transmissions. And I believe that based on these numbers, the first phase of the Terahertz communication research is going to the end. And we are now at the point of, we are now at the starting point of new 6G communication system. I like to say this second phase of communication, Terahertz communication research. Then what do we need to do? So probably once we need to think about the beamforming transceivers. I didn't mention that much in this my dear talk, but because of very high directivity at high frequencies, once we need to steer the beam directions, to extend the beam service coverage at high frequencies, then when we need to have as a beamforming transceivers. This is the mission number 1 if you are the RF engineers or RF circuit designers. If you are system engineers, then probably we need to think about how we operate the Terahertz communication system. I have demonstrated the QAM or QAM waveform at for 100 gigabit per second data transmissions, but we need to operate very carefully because usually QPSK requires very high signal to noise ratio compared to BPSK or any other wideband waveform. Then we need to think what is the appropriate operating point in channel space, the power limited one or bandwidth limited one. It is very important when we develop the practical Terahertz communication system. And finally, I mentioned very shortly about the CMOS technology for Terahertz applications. That is quite true because CMOS is very powerful to implement very multiple functionality in single RFICs. But in terms of power and noise figures available from those devices, well, regardless, probably we need to incorporate such a CMOS very high functionality CMOS RFICs along with the very high performance 3.5 electronics. Then the question is how to integrate that. So my answer would be there might be one option to integrate those two different material technology in wave level 1. So here is my brief suggestions in future research in Terahertz communication system. Okay, so this is everything I prepared for you today, and thank you very much for your kind attentions, and I would be more than happier to have any questions from you. Thank you very much.
Thank you very much, Dr. Sung, and I would like to open this presentation for answers. If there are any questions, kindly put them in the chat box, or you can directly ask. A few questions that I can read from the chat box. One question is, can we magnetic wave nature?
I'm sorry. So the question was about the radiation efficiency of the antennas at Terahertz band. Oh, is it okay? Do you hear me?
Yeah.
So regarding the antenna efficiency, actually today I presented two different types of. Go ahead, please.
From Dr. Shamak Bhattacharya, can you comment efficiency of the antennas?
That's right. Yes, radiation efficiency. So, probably I may confuse. I'm looking at the chat slide, and the question from Dr. Shivada was about the radiation efficiency. So, is it okay to talk about this?
Yeah, sure, please. If you can read the chat box, that's fine. Please.
All right, okay. All right. Probably I confused. All right. Anyway, first of all, regarding the radiation efficiency, it was quite hard to directly measure the efficiency numbers from, but according to the simulation result, in case of the on-chip antennas, once you place the dielectric range on the backside of the on-chip antennas, then radiation efficiency would be around 60%, 60%. And also in case of the very compact horn antennas based on the plastic packaging one, there was a measured one. The measured radiation efficiency was estimated to be around 80% or even more. So in case of the conventional commercially available horn antennas, waveguide packaging horn antennas, the radiation efficiency is estimated to be around 85% or more.
Right, and there's another question, like to achieve dBi of antenna gain, what might be the antenna size at terahertz?
Okay, so as I said before, in case of the horn antenna, the diameter would be around 8 millimeters. Diameter of horn antenna would be 8 millimeters for 25 dBi gain. So that is easily achieved with mechanical machinings. Okay.
Right. And should the characteristic substrate considered in the terahertz domain?
Well, that is a very important one. So as I said before, in perspective of RFIC or MMIC, so because of very high dielectric constants of around 9 to 12, all the electromagnetic energy used to accumulated in substrate or guided in substrate as a substrate mode, or let's say a T mode or TM mode or something like that. But this is very serious issue because the desired signal should propagate along with the microstrip line in circuit or a CPW line along with the circuit, but they can be there is another parasitic path. So this one actually degrade a lot the energy efficiency or gain efficiency of the circuit. So in that perspective, the substrate should be, dielectric constant of substrate should be as low as possible. But unfortunately, many semiconductor material, in case of semiconductor materials, the dielectric constant is so high. So I believe that, yes, simply speaking, we prefer to have very low dielectric constant substrate even for MMIC, but unfortunately, such a material is not that available in near world. But okay, so that is my one short comment. And in case of antennas, it is obvious the low dielectric constant material is very, very helpful for to have a high dielectric constant. The high radiation efficiency. But in my experience, the more important one is that the dielectric loss. So once we design the antennas or many other the passive devices, the dielectric loss caused by the substrate was very huge. So that once we select, when we select the materials, the key parameter I'm focusing on is the tangential loss rather than the dielectric constant.
Right. There's another question. Can you comment on challenges faced in generating high power terahertz?
Oh yes, it is extremely the challenging one. So in case of the power, even in the power amplifiers, simply speaking, if we integrate more transistor in single power amplifier, then theoretically we are able to get more powers. But as I said before, because of the serious heat issues, once we integrate more transistors, the probability of the failure to heat gain dramatically increases, so that technically we are not able to get more power more than the 1 watt. The 10 dBm at this moment in my group, at least in my group. Then actually the design challenging is changing to how to deal with the heat problem rather than the how to effectively combine the power from single transistors. So that shortly speaking, if we can deal with the heat from the core MMIC, then we can increase the power more and more. So in that point of view, the waveguide packaging is yet one validated solutions to deal with such a heat problem.
Right. There's another LTC's packaging limitations by selecting antennas to be fabricated.
So the, all right, go ahead.
Yeah, please go ahead, sir. Go ahead.
Okay, so the biggest challenge of LTCC, right? So I guess the two. The number one is the fabrication tolerance is not that good for Terahertz applications. Usually, the LTCC technology is strongly rely on, let's say, the thick film process. The metallization is based on the some sort of the printing technology. And also the alignment between the multilayer is also based on something, the mechanical, the alignment technology, so that basically the tolerance, fabrication tolerance of LTCC is in order of 30 micron or 40 micron meters or something like that. So those numbers is quite, I mean, challenging to realize very highly accurate antenna structures, so that I would say the limitation number one is a fabrication tolerance of LTCC technology. And also the number two is if you are interested in the antenna design, the dielectric constant of LTCC, for example, 7 or maybe the lowest number would be around 5 or 5.1 something. So even though dielectric constant is a little bit high to get low enough, I mean the high enough radiation efficiency at these high frequencies. So again, once again, because of poor tolerance, I mean the fabrication tolerance and the poor metal surface, it is quite hard to suppress the parasitic field in the antenna structures, and also the high dielectric constant actually harder to get the high radiation efficiency, and also it is rely on it depends on the vendor of LTCC film, but in general the tangential loss of LTCC film is not that superior to the other materials, so that basically yes, the LTCC is very attractive to implement very, I mean the new structures of the antennas, I mean three-dimensional structures of antennas, but simply speaking, just for the best performance, the LTCC is not that good solution, I guess.
Right. So we may look into some other solutions too. And the efficiency of power at Terahertz frequency.
So just that in case of our amplifier, it can produce 10 milliwatt while consuming 1.3 watt. So simply the energy efficiency would be around 0.8, anyway, less than 1%.
Yes. That's than 1%. There's another question, like suggest a low cost, actually 85% efficiency at Terahertz and low cost substrate.
Yeah, it's quite a difficult question, I guess. So if we really like to have such a high efficiency at Terahertz frequencies, then I would suggest the quartz substrate, but you know that the quartz is not that the cost effective. Then the second option would be simply glass one. The fused glass ones, fused glass substrate actually provides good enough loss property and low over around 4 or 3.8 dielectric constant, and very mechanically very strong. And I believe that by carefully designing and the measurement, probably you are able to get around 85% radiation efficiency. But there is no good many options in terms of antenna topology. That is one big problem.
Right. Thank you so much. as you can see, most of the were related to antennas, right? Because we have lots of antenna researchers here, I think, attending
No,
seminars.
right.
Personally speaking, I have a question. I was to see that quasi-optical packaging. As you said, the problem we have this LED, like a quasi-optical available out there in the current state-of-the-art technology.
Okay, yes, very important one. So, as I said, this is a very general and conceptual diagram of the quasi-optical packaging. So, to realize that actually the antenna and the packaging should be separated in somehow. That's because in our case, please note that the silicon range is placed right on the back side or back surface of the MMIC. So actually, mechanically, this lens and the MMIC or the on-chip antennas are touched. So when we assemble the silicon lens on the back side of MMIC, we experienced lots of failures due to the mechanical stress or mechanical, the force heading to the MMIC. So we need to solve that. So now we are thinking to add some kind of the supporting material around the MMIC, to get the, to make the mechanically supportive. So there is remain the issues, but in general speaking, the quasi-optical technique is very attractive because of the low-cost packaging available, and also we didn't need to add any wire bonding or any the electromagnetic loose materials in the Terahertz passes. So that I believe that if you are in the antenna scientist, and this kind of let's say the quasi-optical packaging or quasi-optical antenna approach is one very interesting research topic.
Right. We literally we don't really do much thought or process in terms of packaging, right? But packaging is a very important issue, especially when we develop on-chip antennas or system integrated antenna devices. That's a very important issue that we should look into. But
that's right. That's right.
There's more question, but once again, thank you so much for.
Can I have a question?
Yes, I will hand over the mic to Dr. Shah.
Yeah, Dr. Song, thank you very much for covering almost a 360-degree coverage on Terahertz technology and talking on some of the future directions. So, related to the introductory slide that you had, from there I have a very brief query. Can you hear me?
Yes, I can hear you. Go ahead.
So you talked about something from that Terahertz transaction article by Dr. Gautam Chattopadhyay. So in that article, there is a concept of cascaded frequency multipliers, using which from a 8 gigahertz signal, microwave to at lower terahertz signal, 1.7 terahertz signal is demonstrated. So according to you, what is the limitation of this technique? So why can't we use it for going to further ahead or producing more power, etc.?
So you told about the Dr. Gautam's research article that is about the frequency multiplier at up to 1.2 terahertz, and your question would be around what is the technical limitations of such applications or in my system. Yeah. So in case of the multipliers, the biggest challenging is energy efficiency. So to produce a high enough power, so multiplier is a very good option to produce high frequency signal anyway. The problem is that we need to have very strong input powers, to make the core device operate in nonlinear manners for multiplied signals. So meaning that, simply speaking, the energy efficiency is very poor. So in that point of view, for example, let's say in case of the 1 terahertz signal, and you now have 100 gigahertz signals, then it's a 10 times difference. But to produce 1 terahertz very high power signals, then probably you need to have around a couple of watt. But 100 gigahertz signal. Yet the 100 gigahertz 1 watt output power signal or amplifier is very challenging. So in that point of view, the getting output power from the multiplier is very challenging. But as you may know that with a very dedicated device from JPL, they succeeded demonstrated very high output power multipliers. So there is a reasonable result, but generally speaking, a serious problem with the multiplier is energy efficiency. So unfortunately, there is no way to avoid such limitations without any good amplifiers or driving amplifier between the multiplier stage.
Yeah, maybe also the phase noise also is a concern as you keep on adding more stages, isn't it?
That's right. The phase noise is another challenge, but theoretically, when we multiply the frequencies from with any number of integer numbers, then there is no way to avoid such degradations. And the residual phase noise is one remaining issues, but considering the general the jitter, let's say the numbers at very high frequencies, the residual, usually you know that the residual phase noise is come from the one over flicker noise of the core devices. And then, but fortunately, the flicker noise from HAMT devices is not that high. So that you don't need to worry about that much about the residual phase noise. But anyway, the degradation in phase noise is quite big challenging in particularly in the frequency communications and radio applications. Yes, that's true.
Yeah, thanks. Thank you very much for coming to this workshop. Over to you, Professor Siddiqui.
Thank you very much. I think we can conclude this session, and so you can. Thank you, Professor Song. It was a very informative talk. That's what I can see from all the chat box. Everybody enjoyed this talk, and it's very important that the state of the art technology and the taste of very moving.
Yeah, we have next speaker also present now, Professor KJ Binoy. So let us welcome Professor Binoy from the Institute of Science and Bangalore. So before we move to the technical part of the second talk, can we have a virtual photo shoot? So all the speakers and the participants are requested to turn on their video. Shivada, you can screenshot.
Sir,
Good morning, Professor Binoy.
Good morning.
Yeah.
Professor Vinay.
sir, can you stop it?
Done, Shivada?
Sir.
So thank you, Professor Siddiqui, for chairing this session, and thank you, Professor Song. We look forward to welcome you in Trivandrum once the pandemic goes and we get back to the normal situation. So Shivada, let us move to the second part of the event.
Sure, sir. Thank you very much, Dr. Ho-Jin accepting our request and delivering such an informative and motivating session on Terahertz communication devices and system. Now let's move on to the second session of our event. I welcome Dr. Sumak Bhattacharya sir, IIT Banaras Hindu University, the session chair of second talk session. Further proceed. Thank you.
Thank you. Am I audible? Yes, from.
Yes, sir, you're audible.
Good morning to all of you, and it's my pleasure to share the session to be presented by Professor Veena. And let me introduce the speaker quickly. KJ Veena is currently the professor and chairperson of the ECE department in the Indian Institute of Science, Bangalore. He obtained PhD from Pennsylvania State University, USA in 2002. Earlier, he obtained MTech in electronics from Cochin University of Science and Technology, Kochi, and BTech in applied engineering and instrumentation from College of Engineering, Trivandrum. He worked at the National Aerospace Laboratories, Bangalore from 1994 to 98. After his PhD, he joined the Indian Institute of Science, Bangalore as an assistant professor in 2003. From Vinay's research interests, Professor Vinay's research interests covered several aspects of RF and microwave engineering, including microwave and millimeter wave antennas, microwave circuits, and his doctoral research on fractal shaped antennas is widely cited. As part of an ongoing project of indigenous 5G development activity, he has demonstrated a